Hello everybody, this is Rob Swatsky from the York campus of Hack, and welcome back to my Biology 121 Anatomy and Physiology 1 course. This is podcast 2.4c, Acids, Bases, and pH. From previous podcasts, we know that dissociation is when chemical substances separate into ions when dissolved in water. An acid is a chemical that dissociates into one or more hydrogen ions and one or more negatively charged anions. For example, when hydrochloric acid, HCl, dissociates in water, it ionizes into hydrogen ions and chloride ions. Some common household examples of acids include lemons, soda pop, and coffee. Acids are also called proton donors because hydrogen ions consist of just one proton having one positive charge. A hydrogen atom in an acid contains one proton and one electron. When it ionizes, it loses its electron and becomes a hydrogen ion, leaving it with its single proton and a positive charge of +1. So when you see hydrogen ions, think protons. A base is a chemical that dissociates into one or more hydroxide ions and one or more positively charged cations. For example, when the base sodium hydroxide, NaOH, dissociates in water, it ionizes into sodium ion and hydroxide ion. Some common household examples of bases include window cleaner, antacids, and bleach. Bases are also called proton acceptors because they can remove hydrogen ions, protons, from a solution. A salt is a chemical that dissociates into cations and anions when dissolved in water, with neither of the ions being hydrogen ion or hydroxide ion. For example, when the salt potassium chloride, KCl, dissociates in water, it ionizes into potassium ion and chloride ion. Many electrolytes in the body are salts that play important roles in the conduction of nerve impulses and maintaining fluid homeostasis. Salts are also the products of reactions between acids and bases. When hydrochloric acid, HCl, reacts with the base potassium hydroxide, KOH, they each dissociate into their ions, which are then recombined in an exchange reaction to form two products, the salt potassium chloride, KCl, and water. The body spends a great deal of time and energy in acid-base homeostasis throughout all of its intracellular and extracellular fluids. Even a small change in hydrogen ions or hydroxide ions is enough to impair cellular and bodily processes. We can determine how acidic or basic a solution is by measuring the quantity of its dissolved hydrogen and hydroxide ions. A solution with a high concentration of hydrogen ions is a strong acid, while a solution with a high concentration of hydroxide ions is a strong base. We can measure the strength of an acid or base by using the pH scale, which ranges from 0 to 14. pH stands for potential hydrogen because it's a measure of the concentration of hydrogen ions in a solution expressed in units of moles per liter. A solution having a pH below 7 is an acid or acidic solution. Its concentration of hydrogen ions is greater than its concentration of hydroxide ions. The lower the pH, the more acidic the solution. Some pH values of common acids are coffee, pH equal to 5, soda pop, pH equal to 3, gastric juice in the stomach, pH equal to 2, and hydrochloric acid, pH equal to 0. A solution having a pH above 7 is a base, or a basic alkaline solution. Its concentration of hydrogen ions is less than its concentration of hydroxide ions. The higher the pH, the more basic the solution. Some pH values of common bases are soap, pH equal to 9, window cleaner, pH equal to 11, bleach, pH equal to 12, and oven cleaner, pH equal to 13. A solution with a pH equal to 7, such as pure water, is neutral. Its concentration of hydrogen ions is equal to its concentration of hydroxide ions. The pH scale is a logarithmic scale based on the power of 10. Each whole number change in pH represents a 10 times or tenfold change in hydrogen ion concentration. So each whole unit change in pH can be written as 10 to the exponent x, where x equals the number of units changed on the scale. For example, a solution with a pH of 5, like coffee, is moderately acidic. If we add a stronger acid to it and its pH decreases from 5 to 3, it has changed 2 pH units. This means that a solution with a pH of 3 is 100 times more acidic than a solution with a pH of 5. Remember that each unit represents a tenfold change in hydrogen ion concentration. So if we lower a solution's pH by 2 units, 10 times 10, or 10 squared, equals 100. So there is a 100 times increase in hydrogen ion concentration. What happens when we go in the opposite, or basic, direction? For example, if we add a base to our acidic coffee and its pH increases from 5 to 8, it has changed 3 pH units. This means that a solution with a pH of 8 is 1,000 times more basic than a solution with a pH of 5. Remember that each increase in a pH unit represents a tenfold decrease in hydrogen ion concentration. So if we increase a solution's pH by 3 units, 10 times 10 times 10, or 10 cubed, equals 1,000. So there is a 1,000 times decrease in hydrogen ion concentration. Thanks for watching, and please feel free to contact me by email at rjswatsky@hack.edu if you have any questions or comments about the course.